Okay, here's the problem that we're trying to work on. We're given two functions f and g. They do have points of intersection at 0.17 and 3.091. And we are supposed to find the volume of the solid that's generated by cross sections, by rectangles that are perpendicular to the x-axis with a base that's between those two curves and has a height that equals 2.5 times the base. Now I'm going to set some data up on Desmos. Before I do that in this video, I want to make sure that you know how to do some stuff. I know you know how to plot functions. If you need to add like a folder, you can click this plus button and click on folder and give the folder a name. And if you want, you can move it up and down, and then you can move things into it. So I just slid that function into that folder, and now I can hide the function by hiding the folder. I can display what's in the folder. If I want to create a table, I can click the plus sign and click table, and it'll give me x sub 1, y sub 1. If I put a value in there for x sub 1, I can change this to f of x sub 1, and it'll put this 3 into the function, and then I can type other values and it'll fill in the function value. So you can also add a note. This is a note, and then plot a particular function or point or whatever under that note. So I could say 2 comma f of 2, and then plot the point. Now, why isn't it there? Because it's way up there. Okay, so that said, I'm going to come back to here, and before we go to Desmos, and talk about how you would set up the definite integral. I think we've already talked about this, that this is the formula for the volume by cross sections, where the cross sections are perpendicular to the x-axis. A of x represents the area of a typical cross section. So this base right here, this could be the rectangle. Or the base of the rectangular solid with a dotted black line in the middle, maybe the midpoint of the thickness of that rectangle. And to calculate the area of that cross section, the cross section looks like this. The base is g of x minus f of x. And if I give that a function name and call it the base, then I can say that the height of the rectangle is 2.5 times b of x. And if I want, I can even give that a function name. And you're going to see that I did this on Desmos. I could call h of x as 2.5 times b of x. And of course, the thickness is a constant in our case. It's always 1/8. That was part of the directions. So the definite integral that calculates the volume of this rectangular solid, or of this solid, I should say, is the integral from 0.17 to 3.091. H of x times b of x dx. And we're going to see that on Desmos. And what we're trying to do is create an approximation for whatever this number turns out to be. So let's go to Desmos. And there's the same graph that I had put on the Ant whiteboard. Here's the original functions defined in the defining functions folder. F of x is the red function down below. G of x is the blue function. And the points of intersection I've labeled A as the x-coordinate of the left-hand endpoint, 0.17, and B is 3.091. And then I've actually plotted those points, A, F of A, and B, F of B. So I got the points of intersection for these two curves simply by looking at the Desmos graph. So I'm going to close that. The thickness constant I called T sub 1, which we're told that that's 1/8. That's going to be the thickness of every rectangle that lies in the base of the area between these two curves. And the starting x value was the left-hand endpoint plus half the thickness. It's like we have a little rectangle right here where S sub 1 is like the midpoint of that first rectangle. So there's the constants. And then I created some functions to actually calculate the length of a base for a given x value, the corresponding height of that rectangle, and we already know the distance, but the thickness. And I also created a function to generate all the x values that we're going to have along the x-axis. So let's see what those functions look like. B of x is the length of a base for a particular x value. By the way, I meant to mention when I defined these functions, I put this in here to restrict the domain. So I just went from 0 to 4 so that we don't have this big, huge graph. And also when I'm up in here, when I created the grid, I unchecked the minor grid lines. You can choose to leave those in if you want. Okay, back to our functions. B of x is the length of a base. The height is 2.5 times whatever the length of the base is. And then the volume of a particular rectangular solid is the height times the base times the thickness. So we're going to have like 22 or 23 rectangular solids lying along this area. And then I created this function called capital X of x to calculate the different x values along the x-axis. So the x sub 0 would just be starting at that S sub 1 value, which was, remember, A plus half of T sub 1, half of the thickness. Then after that, we start at S sub 1 and add on 1 thickness. So x sub 1 would be the second x value, x sub 2 would be the third, and so on. So I'm going to hide these functions. And then in this folder, I did display two typical bases by saying x equals S sub 1, that's this little line right here. And I restricted the domain to have a y value that's between f and g of the x value. And then I did another x equals x sub 12, the 13th x value, and restricted y so that I could get this black dotted line. That's just to help you visualize what the base of a rectangle looks like. Okay, and then here's the key table. I inserted a table. The first value is called x sub 1, and then I changed the column heading to b of x sub 1. So this value right here is the length of the base for the first x value. And h of x sub 1 is the height. And the volume, we know, is base times height times the thickness. So the volume of that first little rectangular solid is like almost infinitesimal. So I don't know how easy that's going to be to create that little rectangle, that rectangular solid there. But you can see then I just filled in x sub 1, x sub 2, x sub 3. These are the x values that again were created using this function right here. And I went all the way to x sub 22. If I tried to do x sub 23, I would get undefined. Why do I get undefined? Because x sub 23 takes me outside the range. X sub 23 is actually at 3.1 something. So it's too big. So that's how I knew when to stop. And then there's this function in the function definition table under stats called total. So you can, that's what I did down here. I said I want the total of the v x sub 1 column. And I got 29.1816. And then I did 2.5 times the definite integral from a to b of g of x minus f of x, the quantity squared, dx. And there's the exact value right there. Look how close they are. So I'm going to stop the video there. If I see you this weekend, we can talk more if you have questions, or if you have specific questions you want to ask before we meet this weekend. If we meet this weekend, be sure to send them along. So I'm going to end the video, post it on Wisant, I'm on YouTube, and also send the link to this Desmos graph.